Hi, my name is Dr. Clement Chumesi. I'm a medical statistician at the Norfolk Department of Medicine. This particular video is to continue on where we left off in the previous video. So if you've not watched the previous YouTube video on the introduction to statistics and data analysis, please kindly watch before you proceed from here. I'm talking about the previous part or session on this particular video. Thank you very much, and I hope you enjoy it. Thank you very much for this. So today, basically, because we don't have much time, so what I'll do is that I'll just spend about 5 minutes to wrap up what I was supposed to do yesterday. So I'll speed up a bit, and again, the videos will be made available on the YouTube channel, so you could learn at your own pace. So try and take some notes if you want, but you don't have to keep everything. You still get access to the slide and everything we do. So 5 minutes for the quick overview left in terms of the presentation, and then we'll do some coding as well. Okay, so one thing I just wanted us to touch on a bit was, so there are instances, like I said yesterday, that most of the we have basically for all statistical methods, either statistical tests or statistical models, we have the parametric and non-parametric versions, right? So it means that for the parametric ones, we said there are strong assumptions that needs to be satisfied. But in terms of non-parametric methods, it's quite robust to those kind of assumptions. And one of the most important thing is that the data or the variable must be normal distributed. If it's a univariate outcome, we expect to achieve univariate normality. And if the data is a multivariate outcome, meaning that several dependent variables at a time that you are testing normality, then in that case, you are going to do test for multivariate normality. But there's one thing that I want us to note, especially we are going to touch a bit on regression bits. But one thing is that most of the times when the original data set is not normally distributed, we tend to do some data transformation. And that data transformation can sometimes affect the overall, even data interpretability and results interpretability as well. So I'll just skip this bit because this particular one, I think I've covered it on my YouTube channel about some of the assumptions of the classical regression. But just a brief one is that we expect that there should be a linear relationship between your predictors and then your outcome variable or your dependent variable, because the regression line is basically a linear relationship. So, but this plot, the top left, is one way of testing visually when you plot your residuals against your fitted values. And we want to see if the red line is fairly straight or fairly horizontal. If it is curvy, it tells that there might be a curvilinear relationship. So sometimes it's not always that a linear regression would work. There are instances you might have to fit a nonlinear regression. Sometimes it could be a polynomial regression and so on and so forth. And then, yeah, so I won't go into all these. I'll just go straight to this bit. So when you are transforming data, remember that it happens. There are instances where your original data set is not normally distributed. But if you take log transform, for instance, the data becomes normal distributed. Statistical, that means that the data is not normal distributed, but it is log normally distributed. So it means that if your original data set is not normal distributed, but its log transform is normal distributed, and the data is log normal distributed. There are instances the original data is normal distributed and its log transform is also normal distributed. But log transformation is not the only data transformation. As a matter of fact, we have some class of transformation called the box and Cox transforms that gives rise to different forms of transformation that can achieve at least normality or improve normality. But if you remember yesterday, I said that there are two sources or reasons why a data might not be normally distributed. And one of the reasons is because of potential of outliers existing in the data, extremely large or extremely small numbers of observations in the data. But we also said that there are instances where the data could also be skewed, whether to the left or right. And if the data is skewed, it doesn't matter even if there are no outliers, the normality might not also be achieved. And if normality is not achieved because of skewness, then no amount of transformation will cause the data to be normally distributed. But most of the time, when the data, the normality is due to, let's say, outliers, then certain data transformation can mitigate or minimize the effect of outliers and we could achieve normality. But when it's skewed, that is not always the case. So here, I just want you to see, like, we considered a certain variable. Let's say we computed, like, let's say, the scores of a certain latent variable, and then we're looking at so there's like the original data, and and so there are other visualizations or visual ways of concluding on normality. So there's something you call the Keckel plot, quanta plot. So it's basically plotting sample quanta. Sample quantas means if you arrange your data set from in ascending order of magnitude, meaning that from lowest to highest. That is what we mean by the sample quantiles. And for each position, we have something called theoretical quantiles, and every probability distribution has its own theoretical quantiles. You don't need to understand the theory, but just to know that if you are looking at Keckel plot to test for normality, the theoretical quantiles you use will be normal theoretical quantiles. If, let's say, you want to know whether a data fits a certain distribution, let's say Poisson distribution, it means you should plot the sample quantiles of that data against the Poisson theoretical quantiles. And we expect to see if the data indeed satisfy that probability distribution, then most of the data points should lie along the line of best fit, as we are saying. But anyway, so that's basically that. But with this one, the take-home message here is this is just trying to show some of the data transformation that exists. So it means that there's something called a zero skewness log transform, where you are trying to make sure skewness is set at 0, and then you're also taking log transformation. And then of course, square root transforms are there. And you can also convert data to set of z-scores, especially when you're doing machine learning bits, where we want to standardize the observations or the features or the variables, especially when they have different scales of measurement. You want to unify them and make the data unitless. So sometimes you convert the data into set of z-scores, and then But for this particular data, no amount of transformation caused the data to be normal distributed. If you look at the p-value, normality test assumes that the null hypothesis is that the data is normal, and the alternative hypothesis is that the data is not normal. So one thing is that we expect the p-value not to be significant in order to conclude that the data is normal. So that's one thing I want to. So here, this is one of the effects of variable transformation and how it can affect data interpretability, irrespective of the field you find yourself. So imagine there was this particular, variable, like what we are talking about. Let's say a score of, let's say, post-traumatic stress score, or it could be any score or immune response or whichever. So here you could see that I was plotting the baseline score, the data collected at, let's say, time 0, compared to the data collected 3 months from baseline. And you could see that based on the original data, there's a positive relationship between these two variables. But after transforming the data using the zero skewness log transformation, you could see it has reversed the order of association. Now it appears that they are negatively related, whereas the original data is positively related. So this is to say, when you are transforming your data, be very careful of some of these things. Otherwise, you could affect the overall interpretability of your data. And if a data is not normally distributed, it doesn't mean that you should force yourself to use methods or parametric methods that insist on normality. That's why non-parametric methods exist, and which are robust to departures from normality. All right, so my last 5 minutes will just touch on some briefly on the choice of regression models. First of all, the take-home message here. So I'm just summarizing. I won't go into all the details here, but that will be the last statement. So we start the coding. So one thing I want you to note is this. In order you understand what regression models actually achieve. So first of all, regression is used anytime you want to see the effect of some predictors or some variables or some factors on your outcome or your dependent variable. If you believe, for instance, let's say you want to know what are some of the factors that determines the immunocompetency of an individual. Let's say if people are suffering from COVID-19, and then the main dependent variable is that we want to see their response to, let's say, the vaccine. But the response to the vaccine, we want to see factors that can influence the response to COVID-19 vaccination. So let's say we collected information about the gender of patients, collected information about their age, information about their previous exposure to, let's say, some SARS-CoV virus or all sort of things. Yeah. And in this case, those variables that we want to see how they predict the outcome, like we said, are called the independent variables. And then the outcome or the dependent variable is the variable that we want to predict. Okay, fine. Or we want to see how those other factors influence it or predict it. Now, one thing you have to note is that there are so many classes or types of regression models. But the question is, how do you know the best regression model for your data, irrespective of if your data is cross-sectional, longitudinal, or panel, or hierarchical? Now, the take-home message is this. The choice of regression model is predominantly dependent on two things. The first thing is that it's dependent on the nature of the dependent variable, whether the dependent variable is continuous, discrete, or if I say discrete, I remember count data, where the data can only take whole numbers. So for instance, number of road accidents, number of, let's say, antibodies in an individual, number of, anytime it's number of something, okay, or something that cannot take up fractional values or decimals, then in that case, that's a discrete outcome. So it means that for the choice of regression model, we said is dependent on the nature of the outcome and the data structure. So for the nature of the outcome or the dependent variable, we mean whether the dependent variable is continuous, discrete, or categorical will determine the class of models. And when it comes to the data structure, if the data is cross-sectional, okay, or the data is longitudinal or hierarchical, it also determines the class of models. Now, let's start with the first bit. When we are talking about the outcome of the data, the outcome of the dependent variable. And this is to say that we are talking about the nature of the dependent variable. If the dependent variable is continuous, then it means that we are going to end up using OLS class of regression, ordinary least square regressions, right? And if the data is, and of course, with the OLS regression, remember there are certain parametric assumptions. If they are not met, it extends to using something like weighted least square regression or sometimes generalized least square and so on and so forth. But here, I just want you to know that when the outcome variable is continuous, the classical model we use are OLS class of regression. Now, when you talk about a dependent variable being discrete, that is, it takes only count data. For such dependent variables, the class of models we use are called Poisson regression or Poisson class of regression. Poisson also has some particular parametric assumption that the conditional mean and variance of the outcome must be equal. If that assumption is not met, then we have a problem called dispersion. It means there's dispersion in the data. Whether the mean is, if the mean is less than the variance or the mean is greater than the variance, then the data will be under, there will be under dispersion or over dispersion. But the most important thing is that if the equality of the mean and variance of the outcome is not met, then we also have class of Poisson regression called negative binomial regression, which I highlighted here, and then quasi-Poisson regression. So these class of regression models are used when the outcome variable is count. It means that the outcome variable only takes up whole numbers. And when the dependent variable is categorical, meaning that it's a categorical variable, then what we use, the class of regression model is called logistic regression. Logistic regression. So anytime you are going to do a regression and the dependent variable is categorical, let's say you are looking at factors influencing the prevalence of, let's say, HIV, meaning that your dependent variable is whether an individual has the infection or not. Or maybe you're looking at factors influencing survival of individuals, where your data is whether they were dead or alive. So in that case, it's a logistic type model. But remember that the outcome could have, the categorical variable could have only two levels, or it could have more than two levels. If it has only two levels, then you can qualify the logistic regression and call it a binomial or binary logistic regression. If it has more than two levels, then it's introduced something called multinomial logistic regression. As a matter of fact, there are also instances where the categories have some ranking in there, some natural ranking. So for instance, let's say your outcome variable is the grade of infection. Let's say HIV. We are looking at grades of HIV infection when we have grade 1, grade 2, and let's say grade 3. Assuming that grade 2 is worse than grade 1 and grade 3 is worse than the other grade. In that case, although it's categorical, which is classically a logistic type regression, you could see that there's some ordering in the categories. In that case, it introduces us to another class of logistic regression called ordinal logistic regression models. Okay, so I just want you to note that the nature of the dependent variable. If it is discrete, it means that, or count data, it means Poisson class models. If it is categorical, you are going to end up using logistic class models. And then if it is continuous, then you're going to end up using OLS class models. Of course, again, these are all parametric assumptions. So if they are not met, for instance, if OLS assumptions are not met, we end up using either GLS, that is generalized least square, or weighted least square, depending on the kind of assumptions that were not met. Okay. All right. So I won't go much into that because we don't have time. But again, if that, now I'm done with the nature of the dependent variable. Now let's come to the data structure. Yesterday, I think we've touched a bit on different data structures, and we said for cross-sectional data, each row of the data set corresponds to a particular individual. But situations where an individual could have more than one row of the data, then in that case, that data is a longitudinal or a panel data. And so it means that, and that's one of the take-home messages. And we said that if the data is cross-sectional, then the class of regression models we use are called fixed effect regression models. So fixed effect in this case, because we don't have any extra variable that introduces anything like any nesting level or hierarchical structure. So it's just collecting information about, let's say, gender, let's say height, age, BMI, and those things for each individual. In that case, where each individual has only one row of the data corresponding to that individual, that is cross-sectional. And in that case, the class of models we use are called fixed effect regression models. And we said fixed effect variables are also variables, basically your predictors or your independent variables. They are also called fixed effect variables. Those are the variables of interest. Okay, so that's fixed effect variables. And we said situations where the data is longitudinal, that we use a class of model called mixed effect models. Now, for the mixed effect models, it is not just for longitudinal data sets. You can also use it for hierarchical data sets. We've already touched on those data structures. If you've not watched that, it will be in the previous video. So try and watch that. So we said that for hierarchical data sets, it means situations where data is nested within larger levels. But even such hierarchical data can also be collected over time. So you could have a longitudinal hierarchical data. And what mixed effect models does is that it's able to capture the structure of that data in an effective way. So this is something I just want us to note. There's another class of model called generalized additive models. Think about it this way. We expect high correlation between your predictors on the outcome variable or the dependent variable. But there are instances where you have a continuous what? And apart from that, there's another assumption that the predictors must be linearly related with the outcome. That's why you're using a linear model. It's not always the case. So situations where, let's say, you have a continuous predictor and you did a scatter plot, okay? You did a scatter plot, let's say a plot like this. Okay, I don't have that here, but we'll see it in the, we will see that in the, how do you call it, in the practice test. So there are instances where your a particular continuous predictor has a non-linear relationship with your outcome, but you notice that the goal is to fit a linear model. So what you do is that we fit something called splines. By splines means we are trying to smoothen out that non-linearity to make that predictor fairly linear so that we can now have assess the linear effect on the outcome. And that is what additive models actually do. So it means additive models are models where some non-linear, continuous predictors that are non-linear or non-linearly related with the outcome are smoothing out to reduce their non-linearity to make them fairly linear. And again, we could have that in the context of fixed and mixed effect models. All right, so this is just something I wanted us to note. So without wasting time, now let's start some coding as well. Okay, so before that, do you have any question? Is there any question for me so that I would proceed to the next phase? Is there any question, please? Hello.
Hello. No, please.
Okay.
Okay.
All right.
No, please. No, please.
Then you can you please yeah, fine. The last thing probably I want to touch on just in a minute is something called quantitative regression. Most people are not aware of this. So I'll just touch on that. Now, let me maximize this. So you notice that all the regression models I've mentioned, okay, the generalized linear models, the generalized linear mixed models. So the mixed models are the mixed effect models, okay, the additive models. All these models I've mentioned, they are basically predicting the mean, okay. It's looking at the expected values of the dependent variable. So they predict the mean of the outcome. Now, one thing we have to note is that we know that since the mean is affected by outliers, so situations where your dependent variable is not normally distributed, okay, apart from that, maybe you are not able to achieve the normality of your residuals, because after fitting such regression models, we expect the residuals. The residuals is just the difference between your true values and your predicted values. We expect that difference, okay, to be normal distributed. If it is not achieved, then what that means is that using the classical regression models would be problematic. Why? Because first of all, normality was not achieved. So you are not going to get a good fit. And if a data is not normally distributed, and we said that if we're doing regression test, statistical test, we said we don't have to waste our time still trying to use parametric methods, which assumes that the data must be normally distributed. We can use non-parametric methods. But what if you are doing regression and your outcome variable is also not normally distributed, and even the residuals from the regression is also not normally distributed? What do you do? So this introduces us to some class of models called quantile regression. What quantile regression does is that instead of predicting the mean of your data, you can predict specific quantiles of the data, meaning that you can predict the median. If so, you can look at the median, or you can even predict the 25th percentile or quantile of your data. You can even predict the 75th quantile of your data. So this is just something I want you to know, that it is not only the mean of your data that you can predict using a regression. You can also do a regression model where you are actually predicting the median of the data. And this is how related. So this graph was just to show that if you just look at the first bit of it, it's just to show how so in this case, the blue here was based on the quantile regression, and then the yellow here was based on the classical, let's say classical regression, and then the brown here, that's the color, was also based on a non-parametric version of the classical regression in this case. And it's just to say how closely they are. This is to say that it's not always that we should force to predict the mean or use the classical regression models, even if there are departures from normality. Especially after doing data transformation, you are still not achieving normality. It means that you can actually predict some quantiles of your data. You can look at predicting the median, and for as a sensitivity analysis, you can also look at factors affecting, let's say, the 25th percentile of your data or the 75th percentile of your data. These are not traditional methods, but it's something you should be aware of. Okay, so now let's end that bit. Okay, so all right, now let's come back to, so basically, if you are new to R software, so we are going to just talk about, do a little programming in R. So one thing I want you to notice that when you talk about programming, there is sometimes a confusion. Like those who are in, those who do computer science, the kind of programming they do, although it's not too different from the kind of programming a statistician or a mathematician would do, I just want you to know that there's a distinction, or there's a difference between statistical and mathematical programming and programming from other fields, engineering and computer science. Those in computer science sometimes develop programming codes to solve, or maybe it could be they are trying to develop an application, and underneath that application are a set of programming codes. But we as statisticians, we do programming with the goal of what? Analyzing data and also trying to test hypotheses, and at the end of the day, answer some research questions. So that is the clear distinction. Of course, we could also have a statistician who is also helping, especially those into machine learning, but they can also develop certain methodologies underneath certain applications and so on and so forth. So sometimes there are intersections, but they are distinct. All right. So if you have downloaded R, you remember initially I told you to download the R base. So this is how the R base looks like. So the R base, you see something called just the R console. So the console, you can type anything. You can use R as a calculator. So it means if you want to calculate, multiply big numbers, you don't need to go and worry about you getting a calculator. So you can use R for all those things, right? But the console is not user friendly, especially for beginners. So I'm just trying to say that anything that I would do in any platform in R, just bear in mind that you can do the same thing in the console. Okay, but we are not using the R base. So this is how the R base looks like. I'm using MacBook. Those who are using Windows, you would also get something similar like that. All right. But one take-home message is this. So when you talk, so let me just close the R base. So this is the R Studio. This is how it looks like. Now, one thing we have to notice that there's something we call integrated development environment. Integrated development environment, bear in mind that you don't need to memorize everything. The videos will be made available. So just get the overview and then you can always watch and practice at your own pace. Integrated development environment is basically a platform that we use to run programming languages, not just R. It means that if you are interested in programming in Python, if you are interested in programming in C++, Julia, or any of Fortran or any of the other programming languages, I just want you to note that there's a platform within which we run those programming languages. So now let's restrict ourselves to R. R is not only run using RStudio. At the end of the day, I'm also going to introduce you to something called Jupyter Notebook. Okay, so I do my R programming using Jupyter Notebook. Okay, and I'll explain the benefit of that. So we'll come back to that. So I just want you to know that there's a platform that we use to run programming languages, and those platforms are called integrated development environment. Okay, and every language, every programming language has its own platforms. Okay, and when you talk about language, as we know, we speak English, we speak French, and all those things. It means that every programming language also has some set of I would say syntaxes or words or languages that is peculiar to that particular programming language. And in order to communicate with that software, you need to know that language. Now in R, you can run R using the R base, or you can, so the R base is one of the integrated development environment or the IDE to run R. So it's just one of the platforms. RStudio is the second IDE to run R. And then we are going to talk about something called Jupyter Notebook. So this Jupyter Notebook, the beauty is that I can run with Jupyter Notebook, you can run over 30 different programming languages in Jupyter Notebook. So for instance, it means that here is because I have only, I have R and Python in here. If I want to run, let's say Julia, or let's say Fortran in Jupyter, I just need to add something called Fortran kernel, and I should be able to. So here, R was not automatically added to my Jupyter Notebook, but I just added to add its kernel, and it helps me to run R here. So I just want you to know that there are so many platforms within which you can run R, but the easiest one is the RStudio for beginners. So like I said, you can use R as a calculator. Okay. Now, in order to use R, the first thing you need to do is to create a script. Why? Because if we type anything here, let's say 100 plus, let's say 30, anything we do here, in case, let's say in some future time, you want to save this results, or if I should close this, I'll lose everything that I did down here. I'll lose everything, okay? So for instance, let's say we created, we simulated the data from, let's say, a normal distribution. So we use R norm, and then let's say we simulated 100 data points, where the mean, we are assuming the mean is, let's say, 1, and standard deviation of, let's say, 4. Have you noticed that once I start typing, it pops up, something pops up? So that's why it is a bit user-friendly, okay? So let's say if I want to, let me generate another one. Let me generate another, I can just copy and paste. And then let's say I've generated another one. And let's say I do some plot X, Y. So here I'm just doing a scatter plot. So you notice that this is where the graph, so it means this part, you see your plot coming up here. If you want to install certain packages, which we'll talk about it, you just come here and you can install them with ease. All right. Now let me just make it a bit complex. So let me increase this to, let's say, 10,000. And let me do the same for X. And let's see, there's going to be a nice shape. So let's say if you want to plot a scatter plot of this, and let's choose a color. So we can choose, let's say, blue color. Now, if I should plot this, let's see what happens. Okay, so we get some elliptical shape like a sun, basically. Anyway, so it means that for our studio, anything that any plot you do, you see it here. Okay, so that's one thing, and you can even export it. You can click on export, and you can even click on zoom. Let me click zoom here. Yeah, you can click on zoom to see the plot in a bigger, view, and then you can click export. You can actually save. You can click save and save your graph in any folder. So here is because I've set working directory to a certain folder, so that's why. Otherwise, you can define the path where you want to save the plot, and you are good to go. All right. So that's just an overview of that. But the first thing you need to do is to create something called a script. The first thing you need to do is to create a script. So here, where we are able to type the code, so here we are able to type things directly here, and we get the results, right? This is called the R console. Now the R console, anything you type there, you lose it forever if you should close R. So the first thing we need to do is to create a script. So to create a script, we click on this plus bit and we click R script. So when you create a script, this is basically, so you get this kind of view. Okay, so now we have this kind of view. And bear in mind that this view that we have, we can actually do the same thing we're doing. So I can actually now type X. And so, but bear in mind that, let me say, I'm simulating a data from normal distribution with 10,000 data points and a mean of 0 and standard deviation of 1. Now, this thing here is called an object. The reason why we call it an object is that it is used to save. It's like a holder. Now, for instance, suppose I didn't have this here, right? And then I wanted to, so if I should run this, I just get basically some simulated data set, okay, from a normal distribution with mean of 0 and variance of 1. But so for instance, imagine if I want to reuse this, I can't use it unless I copy the whole thing and use it again. But if I now assign this to, let's say, X, you can either use equal to, or in R, you can bring less than and this. Okay, so this sign, less than with the dash sign, is actually the same thing as using equal to. It's used for assigning. Okay, so now the moment I run this, to run this, you can either highlight and click run here, or you can put the cursor at the end of it and click run. Okay, now let's do the same for so I'm now using a different object. Okay, so here you can use any name. Okay, I can even type Clement, but bear in mind that there shouldn't be any spacing. If you want to do any spacing, you should rather use underscore. Okay, so never space as an object. So meaning that if you are creating an object name, make sure there's no space. You can use underscore if you want to make the name longer. So let's say I'm simulating another data from normal distribution. Everything will make sense very soon. Just a minute. So at the moment we are just exploring. Yeah. So if I should run this, okay. So what that means is that anytime I run X, okay, if I click run X, or you could use print X is another way of also printing the output. So anytime I print X or I run X, you now see that I get the output, okay? And it's because I have saved this into that holder. So that holder is called an object. So in programming, if you hear object, it's just to say that it's like a saver, or it's like a holder that is holding something. And it could be holding a data, it could be holding a complex structure, it could be holding anything. Even sometimes it can be holding a graph or something of that sort. All right. So it means that now I can plot, do the same plot I did, XY, and I can choose, let's say, red color. I can choose red color, fine. So if I should run this one, now I have that. So imagine if I want to save this script, because you'll be writing very long scripts, creating functions and doing complex things. But the most important thing is you need to know how to save it. Okay. So first of all, before we save, anytime you are doing R programming or anything of that sort, the first thing you need to do is to create a folder. Even if you want to import a data into R, the most important thing is to create a folder. The folder you are creating, we are going to call it a repository. So anytime you hear working a repository, or when you hear working directory, it is just the folder you've created. So I created a folder. Okay, let me look at the name. I created a folder. I just called it Empowering Women Researchers folder. Okay, so I just created a folder. So if I open this folder, it means that if I want to import a data, I have to make sure that the data I'm trying to import is also inside that folder, because that folder is basically going to be your working repository. So it means that you can, anytime you want to import data into R, the first thing you need to do is to make sure your data is sitting inside that folder. And then there are instances, results that you produce in the R software, you can also export it back to that repository. So that's what we are going to learn. We are going to learn how to import such data set. Okay. All right. So inside that folder, I've created another folder called data. So if I should click on this one, we will notice that we have so many data in there. So I have data, which are data in SPSS. I have data in Stata. I have SAS data. So we are going to learn how to import different data structures into R. Okay. We are going to learn how to import different data structures into R and everything. So we would do that in just a minute. But the most important we need to know is that you should always create a folder where you will save your data, or you want to export your results into R. Now, when you save your data, there's something called working, the path of your working directory, the path. So what is the path? So those who use Windows, you notice that anytime you open your folder, there's when you come up here, there's a place you can click, and you see a path, like you see like an address. Those of us who use MacBook, we can only do that when you click get info, and then we come and copy this bit. And then if I should come to, let's say, if I should come to R here, and I should paste that. So you get this kind of path, right? Those who are using Windows, you see something like a C with that, and maybe it will say desktop, and those kind of things. We'll see that very soon when I go to the main platform I'll be using for this session. Yeah, so the most important thing is that to set import a data and to set working directory and everything, you need to first of all make sure that you have to create a folder. Now, let's say if I want to save this script, all I need to do is do it like the normal way you save anything. You go to File, you go to Save As, then you go and locate that particular folder, and then you can give any name you want to give to it, and that is it. So once you click Save, you would have saved that. Okay, so for instance, let's say I want to save this as my first script. I'll go to Save As, and I'll go and look for that folder called Empowering Women Researcher. Any folder. So in this case, I want to call it my first R script. Remember, when you are saving, of course, you can decide to space it, but usually it's just nice just to use underscore. But when you are saving, you don't. I mean, even if you space it, that will not be a problem. Fine. So this is just to say that anytime you are creating a script, okay, you should make sure you should be able to save it. And anything you write in your script, when you run it, you get your output coming here, and the code will come down at the console. So it means, for instance, let's say if I want to find the mean of X. So it means the mean of X is that I want to find the mean of this data. So in this case, if I should run this one, you realize that the code pops up in the console and the results is just down here, right? And then if I want to find the standard deviation, it's SD, standard deviation of X. And if I click on that, you see the code, the code coming down there. So it means that the console, this part is called the console. This part is your script. This is where your graphs will come in, and so on and so forth. So that's just the message I want you to note. Now, there's something called R packages. Now, R packages are, so we are going to learn, because we don't have time, and I've covered most of these extensively on the YouTube channel, but there's something called functions, right? So there are instances where, let's say you want to write your own function that would take any data set, return the mean, median, mode, standard deviation at the same time. Okay. So for instance, I can decide to create my own function. That's the beauty about programming softwares. Because if you're using softwares like SPSS, Stata, even Stata is a semi-programming software, but it's not a programming language. But if you're using something like SPSS or those in clinical or medical fields, you mostly use something like GraphPad Prism. So you notice that the functions, you can only use functions that the software allows you to. You can't do anything more based on your special needs. So let's say I can decide to create my own function. So this is how we create functions in R. So for instance, I can say that I want to create a function that will return the mean, the median, and the mode. Okay. So what I'll do is that I'll bring this hashtag. This hashtag is a way if you want to write comment. Okay. So it's always good to comment your code so that you know what you're doing. So for instance, if I send you this script, if I add this comment that's simulating a data from normal distribution with, so I'm simulating, let's say, 10,000 data points, okay, from a normal distribution with mean 0 and standard deviation of 1. So you notice that in this case, if I give you this script, you know that, oh, okay, so this line of code, I was trying to, this is what it's trying to achieve. So this is what we call adding comment to your code. You should always add comments so that in some future time, you know exactly what you are trying to do. Or if you should send your code to your supervisor or to anyone, the person will know what you're trying to do. So now we are going to learn how to create, let's say, functions, some specific functions that you want to create on your own. So this case, this is how we create functions. So for instance, let's say I'm writing it my function. Okay. So my func. I can give any name. Like I told you, this is, in this case, is also an object. So anytime I want to create a function, if I have a data, I have to assign an object to it so that, or something to hold that information, so that anytime I need to recall it, I will just run that object and we are good to go. So I'm calling it my function. Remember, I can either use equal to, or I can use the less than and this, okay? Just that sometimes we use this to confuse those who are doing Python, especially if you want to tell them that R is fancy. So we rather choose to use this, but this can be replaced with equal to, okay? All right, so I'll stick to that. Then you type function. You notice that once I start typing, it pops up, so I can even click on that. And then to create a function, you also open something called your curly bracket. So this is how we basically create function. Inside here is something called argument. So argument means that it could be a data you want it to hold. It could be, so in this case, if I write X, I can write anything. Okay. So I'm just using X here to represent a vector of data set. Remember, this data set, when I printed it out, it looks like a single array of data. So it's like a vector of data. Okay. So it means that here I'm assuming that it's just a vector. Imagine if I wanted to create a data frame of this. I could have typed data dot frame, okay, and say that anytime you see, and say maybe this is X data or X values or any name I want to give, and equal to X. I can do the same thing for Y and say equal to Y. Remember, the object here is what I've specified here. So the data is this X, but I'm giving a name to it and I'm calling it X values, okay? And then for the Y, I'm calling it Y values. If I should run this one, you see that it has now converted it into a data format. Let me come up here. It has converted it into a data format. But if I want to record this one, then it will be advisable to save it in a holder. So I'll call this one DF, so data frame. so that if anytime you save it in a holder, when you run it, you notice that nothing pops up because you've saved it in there. But now if I should run df, I'll get it. If I want to see the first row of the data, I can just type head, and that will give me the first 6 rows of the data. If I want to see the first 10 rows, I can bring n equals 10, and that will help me to see the first 10 row of the data. So this is also another easy way you can even create data inside R and so on and so forth. But here I'm just creating a function. And so the function is there. So if I wanted the arguments to take on a data, then I would have specified, even if I specify X, I'll I would define X as my data, right? But for now, I'm just defining X as a vector. So the goal is we want to create a function to return the mean, standard deviation, and let's say median. Okay. Yeah. So all I need to do is, so let's say to find the mean. So I'll say mean. Bear in mind that mean is a standard function in R. So never use a standard function as an object. Because the moment I say mean equals something, I will lose the original definition of mean inside the R function. So I'm just trying to say that anytime we have a default, so for instance, if I want to find a median, you notice that median, once I start typing MED, median pops up. It's a default function. So if I want to find a median, it wouldn't be advisable to use median as an object name. I should rather say maybe median value or something of that sort. So that here I can say is the median, we are finding the median of X, okay? So if I want to find the mean, because the mean is a default name, I can only say mean value, right? So here I can write mean. If I click this mean, have you seen that it always opens up something? So that's why every function, it takes up some argument. So if I'm creating this one, I will end up, if I want to further use this one, I will end up using it and open that circular bracket. Okay. So it means anything here inside this one will be the argument. Okay, fine. So always when you create a function, that is why even if I'm plotting something, I bring that circular bracket, and then I just specify its argument. Okay, so that's basically something we have to know. It means a function has an argument. Argument could be more than one. It could be series of arguments, and it could return more than you need. It depends on whatever you want. So here I'll specify the mean of X, and to find the standard deviation, so I'll call it standard SD value, and then in R I will use the less than, and that I told you it also means equality. So here I'll use SD. SD means standard deviation, and then yeah. So now I want to return the mean, the standard deviation, and then the median. So all I need to do is to bring return, and then I can return it as a list, and I can return it as a data frame. So imagine if I wanted to return it as a data frame, I'll use data.frame, okay, and then I'll write mean value, and then I'll bring median value, and then I'll bring SD value. And so here I can choose to give, I can choose to name this how I want it. I can maintain the name. I can just say mean equals mean value, or I can say this is the mean of X. I can give a different name to it, okay? Or I can say me. Even from here, I can write me, but I think I'll just maintain the same object name. So it means you can use the same object name here or not. Okay, you can change it. So here, so now what I've done is that we have created our own function, and I told you every function you need to specify argument. So, and if you're creating function, you create it according to your specific needs. If R already has that function, then there's no need to create your own function. You only create your own function to do complex things that there are no functions in existence to produce that. Okay. So just that I know we have a function in R called SD to find the standard deviation. We have mean to find the mean. We have median to find the median. but there's no function that will return all these three at a go. So I'm creating my own function to do that. Now I've created a function, right? I told you now we are returning it as a data frame. So the first thing to do is to run this function. So you can highlight the entire function and click run, or you can come to the last curly bracket here and click run. Okay, it also runs the function, but just to be safe, but be careful that you don't highlight. So for instance, suppose I was highlighting this and I forgot to highlight the last curly bracket. Let's see what happens. If I run this, you see there's a plus here. And in that case, it means if I now try to run even this one, now it works. But at the end of the day, if I have, let's say this, it didn't end. If I try to find standard deviation, you notice that it still didn't end. It didn't even produce any results to me. It's because I need to end it or close it. So I can bring the curly bracket to close it. Fine. So now all you need to do is to run that. If you create the function, you run that. And now it appears in your console. This is why you don't need to type or create your own function inside the console directly, because since we've created it in the script, we can always save it. Now, if I click Control S or I click File and click Save, automatically I'll not lose it. I've saved this in that folder that I created. So now let's see how this works. So the function I've created is called myFunc. You notice that the moment I started typing it, it popped up. So I just select it. It will never pop up if you are using Jupyter Notebook or you are using the RBase, okay? It is only RStudio that gives you that functionality. And that's why it is user-friendly, especially for beginners. Now, remember, I created a certain data called X, or a variable called X. So X, let's say if I want to see the first six values of X, I can bring a square bracket and type 1 to 6. And if I should run this one, it will just print out the first 6. If I want to print the last, for instance, if let's say I want to print the first, the fourth, and the C's, I will bring a C. This C is called concatenate. Okay, it's what we use to specify something that we are of a particular column of a data or a particular position of interest. So you bring that concatenate sign. So if I put 1 here, I put 5 here, I put 9 here, it means I'm looking for the value of X that is on the first position, the 5th position, and the 9th position, and that will return it for me. Okay. Anyway, so here we know that X is just like it's a whole data. It's 100 data points that are from a normal distribution. Fine. Now, if I click, remember when I was creating a function, the only argument is the X, right? So now if I bring my func, which is the function, and I specify X, if I should run this one, it now produces the mean value here, the median and the standard deviation for me. Okay, so here I printed it out as what? A data frame. I could have also returned it as a list. What we mean by a list is that if I change this data frame, if I change this data frame to list, okay, in this case, I will comment on that. Remember, anything in comment, R will not see it as a code anymore. The moment you bring the hashtag, it doesn't see it as a code anymore. I told you hashtag is used to do what? Is to use to write comment. So when you're writing comment, of course, you can now space it. Imagine if I should copy this one and paste here. If I run this, I'm going to get error. It says unexpected because R will not see this as a function. I told you it doesn't expect spacing and all sort of things, right? So, but I was just writing a comment. So I just needed to bring what? My hashtag. In that case, if I should run that, if I should run just this hashtag, okay, or let me just select that. So if I should run that, then my hashtag pops up, okay? And in that case, it doesn't bring any error. Okay, so now if I want to return as a list, I just have to change the data frame to this. Now let's rerun the function again and run my func. And you notice that now it has also returned the mean, it has returned the median, and it has returned the standard deviation. Suppose you just want to print out the median. So it's better to save this in an object, right? So assign an object name. So I'll say that my resource, I'll call it my resource, and then my resource, and and then run that. So if I run this one, of course, you can now run or print out that object name and everything inside it will come up. So suppose I want to now extract just the mean value. I can just type that and bring a dollar sign. You see, the moment I brought the dollar sign, it's giving me these options to choose from, whether I want the mean, the median, or the standard deviation. So I can choose the mean, and if I run that, it will print out just the mean. So this is just something I wanted you to note, that we can use R to create our own complex functions. So for instance, those who will be doing PhDs and future time, there are instances where you are supposed to, you read a paper, the paper created a certain complex formula that can be used to achieve, or maybe the formula has integrals, it's just complex, but at the end of the day, you need to evaluate it in a programming software to get your results. And when it happens that way, it means you can create all those functions from scratch. So there are YouTube videos that are already on my channel where we've learned how to create your own functions from the beginning. Okay, so one important thing I need you to know before we quickly go through the practice tasks is that it's about packages. So you see here, I've created my own function, and now I can also create something called a package of this function. So that and when I create a package of this function that I've created, okay, it means that if you are able to install that package in your software, wherever you are, you'll be able to use this function that I created, and I'll be the author of that function, okay? But there are also instances where people or other authors have written their own complex functions to achieve complex tasks, okay? And in order to achieve that, it means you need to install that package, because those functions can only be uncovered once you download or install that package. So in order to install packages, we always you click on package, and suppose, and then you click on package. After clicking on packages, you notice that there are certain names here. All these names are packages that are by default installed. It means that anytime you install a package in R, or anytime, you want to install a package, some packages were installed by default after you downloaded R, okay? So it meant that you only install packages when you are interested in what? When you are interested in making use of the functions inside that package. And to do that, you click install. And let's say we want to install a package called mass. So you start typing mass. You don't need to know then all the names of the packages that you need to install. So just that anytime you need to install a package, just know that this is what you go through. So let's say the package is, let's say, mass extra. Okay. One way of knowing that I don't have this package in R is that, let me close this one. So there's something called library. So when you type library is a way of loading the package to use. So was it mass extra? So this was the package. Now, if I run this one, it tells me that there's no package called mass extra. Imagine if there was a function in this package that we needed to use. So all I need to do now is to come to packages, click install, and type mass extra, okay? And I click install. Remember, you need an internet to install. And the moment you get messages like you get the downloaded binary are now in this, like it means it has installed. And if a package is installed, once you start typing, it will also pop up. So if I start typing mass, then this pops up. Now, if I should click run, you notice that I didn't get any error, and it means that it has successfully been installed. Is there
So we have about 5 minutes more.
Oh, okay, that's fine.
So if you could please wrap up first, that would be great.
All right. Okay. All right then. So now let me come to, all right. We don't have time because anyway, so basically I was going to use the Jupyter notebook to take us through, and all the codes you are seeing here, you can literally copy and paste into your RStudio. You can create your own script. Now you've learned how to create a script. If you come here, you know how to. So everything we've done here, I can click file and click save. I've saved it into my repository. I can always use it. So bear in mind that I use Jupyter notebook to teach, because as you can see, you can write the code, and the graph, the plot, or whatever output will come just beneath it. Imagine if I want to show my results. If let's say you're doing a PhD, you've done some tasks and you want to show your results. You don't need to now create a separate Word document or PowerPoint just to save your results. And especially those who use SPSS or Stata or even or other softwares, you notice that anytime you run a code or something, you now have to summarize your results in, let's say, Word or Excel or something of that sort before you can present it to your supervisor or anyone. But with this one, with the Jupyter Notebook, you get to see everything. So it means the code is just there. And so, for instance, the code is there, and then you see the plot and everything, and it's automatically saved. You don't need to save the graphs elsewhere. All right. So unfortunately, what I wanted us to go through, which time was not going to permit, was that we're going to, first of all, I think I've already introduced what mathematical or statistical programming is about, and I've touched a bit on IDEs. And what are IDEs? I said they are just platforms to run R. And I told you R-based, R studios are just one platform to run R. Jupyter Notebook can be used to run not just R, Python, and other things. So the next set of code was just going to show you how to import and export data. Okay, so we are going to learn situations where you have data in SPSS, but you want to do every analysis in R. So it means you can actually import your SPSS data into R. If you have data in Stata or data in SAS, okay, or the data is a text file or Excel data or a CSV file, we are going to look at how to import all those data sets. The code is written in a nice way. So it's something that once I'll send something. So for the Jupyter Notebook, if I go to File and I go to Export As, the moment I click on executable script here, it will be like the same way you would have saved your results in. Let me just click on that. So if I should click on that, it has downloaded. Now, if I come to my desktop, it will just open like the normal R script, the script I created in R Studio. So it means all the codes I've written, you could see I've literally downloaded all of them here. It's as if I did everything in R Studio and I saved it somewhere else, right? So that's one of the benefit of Jupyter Notebook. Apart from what you are seeing, that you see your codes and your output and everything, you can also download it in different formats. I can also download it as an HTML file. For the HTML file, if I come to my downloads, if I click on this one, and this is what I'll send it to you. So you notice that for the HTML file, all the links can be clicked. So you can click this to access my profile if you want. If you can also so if you come down, everything is automatically saved, just that you cannot edit, but you can copy and paste into your R Studio, okay? So it means that all the results, so it's such that anything you run, you know what it was trying to achieve. And I've added comments for you to know what each code is trying to achieve. All right. So because we don't have time, I think I have about 1 minute or so. So quickly, it means that in some future time, there are certain analysis that SPSS or Stata cannot do. So for instance, in SPSS, you can't do machine learning. So when it comes to a point where you need to use machine learning for, let's say, classification problems or for regression, it means that maybe the data you wanted to use was in SPSS. It doesn't mean you have to convert it to Excel before you can use it in R. You can actually import the SPSS data directly. So I think I was telling you about setting working directory. I told you create a folder. And if you create a folder, it means that if you want to import any data, put the data inside that folder. If I a Windows user, anytime you copy that directory that I was telling you about, is if you go to a folder on your desktop, okay, I'm using MacBook, but if you created a folder called, let's say, Empowering Women Researchers, if you click on that, I told you that in Windows, you can click the upper part here. It will be able to make you see that a full address. When you copy that address and you come to R and you paste, you get something like this. When you paste, it will look like, let me come down here. When you paste, it will look like this. Okay, it will look like this when you paste. It will look like this. Okay, but you have to change this backslash to /. Those who use MacBook, it's automatically / for you, so you don't need to worry about that. Yeah. So when you change it to / and you use something called set WD, it means you are setting working directory. If I should run this one, okay, it means that automatically I have set my working directory and I can import data directly from my folder. So now if I had a certain CSV data, CSV is like a form of Excel data where you've changed the extension to .csv. But we don't have time, so I don't want to go much into that. But they are already so probably let me just come to the YouTube channel briefly and then explain. So you can just search for Clement. But if you get access to this script, once you click on that, it will also take you directly to the videos. Okay. So on the videos, if I've already covered, so there's already an introduction to R programming from scratch. So everything that I was doing, there's a beginner and then it gets complex from one video to the other, right? So you can start that. And you can even, especially if you want to learn how to use the Jupyter notebook to do these kind of things where you have your code, your script, you can write comment, you can do anything. So it means I can write comment. You can actually use Jupyter notebook to submit assignments. You can even use it to make presentation without the need to do PowerPoint and also all sort of things. So from here, if you want to know the most important information to know about statistics is there. If you want to switch from RStudio to Jupyter Notebook, it is also there. I've also covered extensively something on regression modeling, how to create functions. So creating functions, your own complex functions from scratch, importing different data structures, whether it's in Stata, SPSS, you want to bring into R, and then how to now use R for your statistical analysis. Yeah, how to use R for your statistical analysis too. Everything is there. So this course is just unfortunate that we don't have much time because we're also going to use R to do a forensic research. So this is like someone who eventually was killed by a knife and a spear. And we want to use statistical approach to predict the weapon that killed this particular mummy. Okay, so I mean, it's just unfortunate, but the course, everything is there. So you'll be able to have access to the course. So I think without wasting time, I will just end here. And in terms of the YouTube video, I'll still wait for this particular, the recording of this, but most of the things I've already touched on are already on my YouTube channel. So I think once you get access to the channel, you can now learn from at your own pace, start from the beginning and watch as you go in. So I am there. So without wasting time, I'll end here. If you have any question, you can let me know. Thank you.
Thank you very much, Clement. Unfortunately, we're not able to cover everything, but we will you'll find time so you take us through this online. So we'll communicate with you. And thank you so much for your time. We really appreciate it. Please give it. All right. So up next. Okay. Are you going to stay with us?
Oh no, I have to attend to something.
All right. I hope you have a great rest of your day.
All right. Bye-bye.
Okay. All right. I hope you all learned something from the short session that's just